Hello, stargazers. Welcome back to Sleepy Science, where we explore the cosmos at a pace that lets wonder settle gently into your mind. Tonight, we're beginning a journey into something extraordinary. Something so small, you could fit billions of them on the tip of a pin, yet so powerful they've built entire worlds, including the one beneath your feet right now. Right now, as you breathe in, you're inhaling atoms that were once forged inside dying stars. The iron in your blood, the calcium in your bones, the carbon that forms the essence of your DNA, none of it was born on Earth. It all came from out there, scattered across the darkness between stars as something we call cosmic dust. And here's what makes it truly miraculous: these particles, invisible to the naked eye, are the architects of everything. Galaxies, stars, planets you all built from dust, so fine it makes beach sand look like boulders. This isn't poetry, this is science. And tonight we're going to discover how the smallest things in the universe create the largest. If you're ready to explore this beautiful mystery with us, take a moment to like this video and subscribe to Sleepy Science. It helps us keep bringing these cosmic stories to you, told softly so you can learn while you drift. And if you find yourself falling asleep before we reach the end, that's perfectly wonderful. The universe will still be here when you wake. Let's begin with a simple, stunning truth. When you look up at the night sky, the most important thing you're seeing isn't the stars themselves, it's what lies between them. For most of human history, we thought the space between stars was empty, a perfect vacuum, a void. The ancients called it the ether. Early astronomers treated it as nothing more than a backdrop, a dark canvas upon which the real cosmic drama of stars and planets played out. But space isn't empty, not even close. Between every star filling the vast gulfs of interstellar space floats a thin but precious medium of gas and dust. And while this material seems insignificant, it accounts for only about 1% of the mass. Between stars, it plays an absolutely essential role in the life cycle of the cosmos. Without cosmic dust, stars couldn't form, planets couldn't exist, life would never have emerged. The universe, quite literally, would be a much emptier, darker, and lonelier place. So, what exactly is cosmic dust? At its most basic, cosmic dust consists of solid particles, incredibly tiny, ranging from just 1/100th of a micrometer to about 100 micrometers across. To put that in perspective, a human hair is roughly 70 micrometers wide. Most cosmic dust grains are significantly smaller than bacteria, smaller than the wavelength of visible light. If you could gather all the cosmic dust from a volume of space the size of Earth, you'd have barely enough to fill a small room. Yet this seemingly negligible material is woven through every corner of our galaxy and every galaxy in the universe. The story of how we discovered cosmic dust is a lesson in how scientific understanding evolves, often in surprising ways. In the early 20th century, astronomers noticed something peculiar. When they photographed certain regions of the Milky Way, they found dark patches, areas where stars seemed completely absent, as if someone had cut holes in the fabric of the sky. These mysterious voids puzzled scientists. Were they truly empty regions of space tunnels through the stars? In 1919, astronomer Edward Emerson Barnard published a catalog of these dark nebulae, carefully documenting their shapes and positions. Barnard suspected these weren't empty voids at all, but rather clouds of some obscuring material blocking the light from stars behind them. But what could this material be? Gas alone, scientists realized, couldn't account for the darkness. Something else had to be there, something solid, something capable of absorbing and scattering starlight. That something was dust, cosmic dust. And the realization transformed astronomy. These dark nebulae weren't holes in the heavens. They were clouds rich with dust nurseries where new stars were waiting to be born. The darkness wasn't absence, it was potential. Fast forward to today, and our understanding has deepened profoundly. We now know that cosmic dust isn't just sitting passively in space. It's constantly moving, evolving, interacting with light and gas and magnetic fields. We've sent spacecraft to collect it, studied it in laboratories, analyzed its chemical fingerprints with spectroscopy. We've watched it form around dying stars and witnessed it coalesce into new planets. We've even found grains of it preserved in meteorites that fell to Earth dust older than our sun, older than our solar system, carrying within it the isotopic signatures of stars that died billions of years ago. And perhaps the most beautiful discovery of all, that poetic phrase you've probably heard, "We are made of stardust," is not a metaphor. It's literal truth. The atoms in your body were not created here on Earth. They were synthesized inside stars, scattered into space as cosmic dust, and eventually incorporated into the cloud that would become our solar system. 4.5 billion years ago, some of that dust stuck together, grain by grain, building up into larger clumps, then boulders, then planetesimals, and finally planets. And on at least one of those planets, that stardust became complex enough to look back up at the night sky and wonder where it came from. You are the universe experiencing itself. Every breath you take, every thought you think is cosmic dust, rearranged into something miraculous, something that can ponder its own origins. But let's slow down for a moment and truly appreciate the scale of what we're talking about. When we say cosmic dust is small, we mean almost incomprehensibly small. A single grain of cosmic dust has a mass measured in picograms, trillionths of a gram. You would need about 10 trillion typical dust grains to equal the mass of a single raindrop. And yet, when you add up all the cosmic dust in our galaxy, it amounts to roughly 100 million times the mass of our sun. That's how vast the Milky Way is. Even its dust outweighs entire star systems. This dust doesn't just float randomly through space either. It follows the invisible architecture of the galaxy, concentrated in the spiral arms where stars are born, thinning out in the spaces between. It forms the dark lanes you can see cutting through the Milky Way on a clear summer night, the shadowy rifts that divide the river of stars overhead. Those rifts are dense clouds of dust, thousands of light years long, blocking our view of the galaxy beyond. And here's something that might shift your perspective when you're standing under a truly dark sky, looking up at the Milky Way. You're not actually seeing most of the stars in our galaxy. The center of the Milky Way, where hundreds of billions of stars swirl around a supermassive black hole, is hidden from our view by vast clouds of dust. Invisible light, we can't see it at all. The dust is too thick. It's only with infrared telescopes, which can peer through the dust, like fog lights cutting through mist, that we can glimpse what lies beyond. So, in a very real sense, cosmic dust shapes our view of the universe. It hides some wonders from us while revealing others. It absorbs the light of distant stars and re-radiates it as a soft infrared glow. It scatters blue light more efficiently than red painting reflection nebulae in ethereal azure hues. It becomes the raw material for worlds. It carries the chemical legacy of stellar generations across time and space. Think about that the next time you see a sunset. The red and orange colors you love so much. That's dust in Earth's atmosphere scattering away the blue light, letting the longer wavelengths through. The same physics applies in space on an incomprehensibly larger scale. Cosmic dust reddens the light of distant stars, making them appear cooler and dimmer than they truly are. Astronomers have to account for this reddening when they measure distances to faraway galaxies, a reminder that even the smallest particles can have the largest effects when there are enough of them spread across enough space. But the true wonder of cosmic dust isn't just what it does to light, it's what it becomes, because dust doesn't remain dust forever. Given time, given gravity, given the right conditions, dust transforms. It gathers, it clumps, it builds. Grain by grain, collision by collision. It grows from microscopic specks into macroscopic structures, pebbles, rocks, asteroids, moons, planets. This process called accretion is how worlds are born. And it all starts with dust, so fine you couldn't see it, even if you held it in your hand. So, tonight as we embark on this journey together, I want you to hold this image in your mind, the universe is not built from grand dramatic forces alone. It's built from the accumulation of countless tiny things, patient, persistent, invisible things that add up over unfathomable stretches of time into everything we see and everything we are. The cosmic dust that drifts through space right now is not separate from you. It's your past and your future. It's where you came from, and it's what you'll return to eventually when the sun dies and scatters its outer layers back into the interstellar medium, carrying atoms that were once part of you back out into the galaxy to become part of something new. The cycle never ends. Creation, destruction, and rebirth written in particles so small we can barely comprehend them, yet so essential that without them, nothing else would exist. In the next part of our journey, we'll travel back to the beginning of this cycle, to the moments when cosmic dust is born. We'll visit the hearts of dying stars and the cataclysmic explosions of supernovae where atoms are forged and scattered into space. We'll witness the universe's most powerful engines of creation and destruction, working together to seed the cosmos with the raw materials for everything that comes next. Every atom heavier than hydrogen in your body was created inside a star. But here's the part that might surprise you. Those atoms didn't just magically appear in space ready to build planets and people. They had to go through a transformation first. A process of condensation, of cooling, of coming together into something solid. They had to become dust. And the furnaces where this happens are among the most spectacular and violent places in the universe. The swollen atmospheres of dying stars and the explosive deaths of supernovae. Tonight, we're going to witness the birth of cosmic dust grain by grain in the final moments of stellar lives. Deep inside every star, a nuclear furnace burns. Hydrogen fuses into helium, releasing energy that holds the star up against its own gravity. For stars like our sun, this process continues peacefully for billions of years, but nothing lasts forever. Eventually, the hydrogen fuel runs out, and the star must change or die. What happens next depends entirely on the star's mass, and it's in these final chapters that cosmic dust is born, scattered into space like seeds from a dying flower, ready to grow into something new. Let's start with the gentler deaths, the stars that go out not with a bang, but with a slow, beautiful exhalation. When a star between about 1/2 and 8 times the mass of our sun exhausts its core hydrogen, it begins to evolve up what astronomers call the asymptotic giant branch, or AGB for short. This is a phase of stellar old age, and it's one of the universe's most prolific dust factories. As an AGB star runs low on fuel, its core contracts and heats up, while its outer layers expand enormously. The star swells to hundreds of times its original size, becoming what we call a red giant, or in more extreme cases, a red supergiant. The surface temperature drops to around 3,000 Kelvin cool by stellar standards, glowing a deep, dusky red. These bloated stars are so large that if you replaced our sun with one, its surface would extend past the orbit of Mars, swallowing Mercury, Venus, Earth, and the inner asteroid belt whole. But size isn't the most important thing happening here. What matters is the wind. AGB stars lose mass prodigiously, shedding their outer layers in a slow, steady stellar wind that flows outward at speeds of 10 to 30 kilometers per second. This wind carries with it freshly synthesized elements, carbon forged in the star's interior through helium fusion, nitrogen, and oxygen from earlier burning phases. As this material moves away from the star, it cools. And when it cools enough, something magical happens. Atoms begin to stick together, forming molecules first, then tiny solid grains. Dust is born. There are 2 main types of dust that form around AGB stars, and which type forms depends on the star's chemistry. If the star has more oxygen than carbon in its atmosphere, which is common for stars with lower masses, then oxygen-rich dust forms. Silicates dominate here, minerals like olivine and pyroxene, the same stuff you'd find in volcanic rocks on Earth, but formed in the wind of a dying star. These silicate grains are typically between 1/10 and 1/2 micrometer across, small enough to stay suspended in the wind, large enough to efficiently absorb and scatter light. But if the star has dredged up enough carbon from its interior through a process called third dredge up, where convection brings carbon-rich material from the core to the surface, then the chemistry changes. When carbon outnumbers oxygen, a completely different type of dust forms carbonaceous dust. This includes amorphous carbon graphite and complex organic molecules called polycyclic aromatic hydrocarbons, or PA8s. Carbon stars, as they're called, are surrounded by sooty halos of this material, and they're responsible for about 27% of the cosmic dust budget. Here's what's fascinating. We can watch this process happening right now in stars scattered across our galaxy. One of the most famous examples is a star called IRC plus 10216, a carbon-rich AGB star, about 500 light-years from Earth. Observations with infrared and radio telescopes have revealed intricate shells of dust around this star, layered like the rings of a tree, each shell representing a pulse of mass loss from the star's unstable pulsating surface. The dust forms so close to the star that it's literally condensing out of the stellar atmosphere grain by grain, like frost forming on a cold window. These AGB stars don't explode. They don't die violently. Instead, they gently shed their outer layers over hundreds of thousands of years, creating beautiful structures called planetary nebulae, glowing shells of gas illuminated by the hot, exposed core of the dying star. The dust they have created drifts outward with the gas mixing into the interstellar medium, ready to be incorporated into the next generation of stars and planets. It's an elegant, almost peaceful process, a slow return of material to the cosmos. But not all stars go gently. For stars more than about 8 times the mass of the Sun, the end comes suddenly, catastrophically, in one of the most energetic events in the universe, a supernova. For decades, astronomers debated whether supernovae could actually create dust, or whether the explosion's shockwave would simply destroy any dust that tried to form. The temperatures in a supernova are unimaginably high, billions of degrees, in the core millions of degrees in the expanding debris. How could anything solid survive that inferno? Many scientists assume supernovae were dust destroyers, not dust creators. It seemed logical. How could fragile grains of dust withstand such violence? They were wrong. Beautifully, surprisingly wrong. The evidence came from a supernova that exploded in the Large Magellanic Cloud, a small galaxy neighboring our own, in February of 1987. Supernova 1987. A, as it was designated, was the closest supernova visible to the naked eye in nearly 400 years. Astronomers around the world trained their telescopes on it, watching as the light from the explosion brightened, peaked, and then slowly faded over months and years. But the real revelation came later when infrared telescopes began observing the remnant. In the years following the explosion, astronomers detected a growing infrared excess, a signature of thermal emission from dust. The dust wasn't there immediately after the explosion. It formed later as the ejected material cooled and expanded. And the amount was staggering. Estimates suggest that supernova 1987A produced between 0.4 and 0.8 times the mass of the entire Sun in dust. In a single explosion, more dust was created than hundreds of AGB stars produce over their entire lifetimes. Where did this dust come from? The answer lies in the layered structure of the supernova ejecta. When a massive star explodes, it doesn't just blow apart uniformly. Different layers of the star, enriched with different elements from different stages of fusion, are ejected at different speeds. The innermost layers, rich in freshly synthesized heavy elements like silicon, iron, magnesium, and calcium, expand outward and begin to cool. Within the first few hundred days after the explosion, temperatures drop enough for these atoms to condense into solid grains. Silicate dust forms from silicon, oxygen, and magnesium. Iron grains condense directly from pure iron vapor. In regions rich in carbon and oxygen, carbonaceous dust and even silicon carbide grains can form. These grains grow rapidly in the dense, cooling gas, reaching sizes of up to 1/10 of a micrometer within just a few years. It's an incredibly efficient process, nature's way of turning stellar death into the seeds of future life. And here's the crucial point: this dust doesn't get destroyed by the shockwave as scientists once feared. The shockwave does pass through the ejecta eventually, and it does damage some of the dust, shattering larger grains into smaller fragments. But much of the dust survives, protected in dense clumps within the expanding debris. Studies of older supernova remnants like the Crab Nebula, the remains of a supernova that exploded in 1054 and was recorded by Chinese and Arab astronomers, have confirmed that large amounts of dust persist for centuries after the explosion. Think about what this means. Every supernova in the history of the universe has been a dust factory, seeding the space between stars with heavy elements locked into solid grains. In the early universe, when the first generation of massive stars exploded, there were no planets, yet no rocky worlds, because there hadn't been enough time for dust to accumulate. But those first supernovae changed everything. They enriched the primordial gas with the elements needed to build planets, and they provided the dust grains that would serve as the condensation nuclei for future star formation. Now, you might be wondering, which process is more important for making cosmic dust? AGB stars or supernovae? It's a question astronomers have debated for years, and the answer turns out to be both, but in different ways. AGB stars are steady, reliable dust producers. They live for millions to billions of years, and during their final 100,000 years or so on the asymptotic giant branch, they produce dust continuously, steadily enriching the interstellar medium. They're responsible for the bulk of the silicate and carbonaceous dust we see in galaxies today, especially in older, more mature galaxies where star formation has slowed down. Supernovae, on the other hand, are rare but incredibly productive. A single supernova can produce as much dust in one event as an AGB star produces over its entire lifetime. And because supernovae enrich the interstellar medium with heavy elements that AGB stars can't make, like iron, nickel, and cobalt, they're essential for creating the chemical diversity we see in cosmic dust. In young, actively star-forming galaxies, especially in the early universe, supernovae may have been the dominant source of dust, simply because massive stars live fast and die young, exploding within just a few million years of their birth. There's a beautiful complementarity here. AGB stars are like the tortoise, slow, steady patient, building up dust over long time scales. Supernovae are like the hare, explosive, dramatic, delivering huge amounts of dust in a single burst. Together, they ensure that the universe is never short of the raw materials needed to build new worlds. But dust production is only half the story. Once the dust is created, it has to survive. It has to travel through space, navigating radiation, shock waves, and high-energy particles that can erode or destroy it. It has to find its way into molecular clouds where it can participate in the formation of new stars. And that journey from the death of one star to the birth of the next is an epic voyage across space and time, one we'll trace together as we continue. If you could hold a single grain of cosmic dust in your hand, though you'd need a microscope to even see it, you'd be holding a time capsule, a fragment of stellar history forged in the heart of a dying star, carrying within its atomic structure the signature of nuclear reactions that happened millions or even billions of years ago. But what exactly are these grains made of? What elements, what minerals, what molecules compose the dust that builds worlds? The answer is more complex and more beautiful than you might imagine, and decoding it has required some of the most sophisticated detective work in the history of astronomy. If this journey through cosmic chemistry intrigues you, a quick like helps us share these stories with more curious minds. And subscribing means you'll never miss an episode of Sleepy Science. We're glad you're here. For most of human history, the composition of cosmic dust was a complete mystery. We couldn't touch it, couldn't collect it, couldn't analyze it in a laboratory. All we could do was observe its effects from a distance, the way it blocked starlight, the way it glowed in infrared wavelengths. But astronomers are clever, and they developed a powerful tool for reading the chemical fingerprints of dust across vast distances: spectroscopy. When light passes through or reflects off cosmic dust, certain wavelengths get absorbed, while others pass through or scatter. These absorption and emission features appear as dips and peaks in the spectrum of light, and each mineral, each molecule, each type of grain has its own unique spectral signature. It's like a barcode written in light, and if you know how to read it, you can determine what the dust is made of without ever touching it. The breakthrough came in the 1960s and 70s when infrared astronomy began to mature. Unlike visible light, which gets scattered and absorbed by dust, infrared light can penetrate through dusty regions, and dust itself emits strongly in the infrared. Astronomers pointed infrared telescopes at dust clouds and discovered distinct features in the spectra that corresponded to specific minerals and molecules. What they found was a cosmic pharmacy of materials, each type of dust grain, telling a story about where and how it formed. Let's break down the inventory, starting with the most abundant type. Silicate dust makes up roughly 62% of all cosmic dust by mass. These are grains composed primarily of silicon and oxygen, often combined with magnesium, iron, and other metals to form minerals. The two most common silicate minerals in space are olivine and pyroxene, names you might recognize if you've ever studied geology, because these same minerals are abundant in Earth's mantle and in volcanic rocks. Olivine has the chemical formula Mg2SiO4 when it's pure magnesium olivine, though iron often substitutes for some of the magnesium. Pyroxene is slightly more complex, with formulas like MgSiO3. Both minerals produce characteristic infrared emission. Features: olivine has a strong feature at about 10 micrometers, pyroxene at around 10 and 18 micrometers. When astronomers detect these features in the spectrum of a dusty region, they know silicate grains are present. What's remarkable is that these silicate grains can exist in different forms. Some are crystalline with their atoms arranged in neat, orderly lattices, the same structure you'd find in a mineral sample on Earth. Others are amorphous with their atoms arranged randomly, more like glass than crystal. The ratio of crystalline to amorphous silicates tells us about the thermal history of the dust. Crystalline grains require higher temperatures to form, typically above 1,000 Kelvin, which happens close to stars. Amorphous grains form in cooler environments, or when existing grains are damaged by radiation or shocks in space. Then there's carbonaceous dust, accounting for about 27% of the total dust budget. This is where things get especially interesting, because carbon is the element of life, and the forms it takes in space are astonishingly diverse. The simplest form is amorphous carbon, essentially soot, similar to what forms when you burn wood or coal, but created in the outflows of carbon-rich stars. Then there's graphite, where carbon atoms arrange themselves in flat sheets stacked like pages in a book. Graphite grains are excellent absorbers of ultraviolet light, which makes them important for shielding molecules in space from destructive radiation. But perhaps the most fascinating carbonaceous materials are the polycyclic aromatic hydrocarbons, or PAHs. These are molecules made of carbon and hydrogen arranged in multiple connected rings, like honeycombs. PAHs are everywhere in space. They produce some of the strongest infrared emission features we observe in galaxies appearing at wavelengths of 3.3, 6.2, 7.7, 8.6, and 11.3 micrometers. When you look at the infrared spectrum of almost any dusty region in space, you'll see these features unmistakable signatures of PAHs. What makes PAHs so interesting is that they're organic molecules, not in the sense of being alive, but in the chemical sense of containing carbon-hydrogen bonds. Some PAHs identified in space, like naphthalene and anthracene, are the same compounds you'd find in coal tar or petroleum on Earth. Others are more exotic, with dozens or even hundreds of carbon atoms forming intricate molecular structures. These molecules can survive harsh radiation environments and extreme temperatures. They're incredibly stable, and they may have played a role in delivering organic material to the early Earth, potentially contributing to the origin of life. Now, here's where it gets truly beautiful. Cosmic dust doesn't stay bare and exposed. In the cold, dense regions of space, particularly in molecular clouds, where temperatures drop to just 10 or 20 Kelvin, gases condense onto the surfaces of dust grains, forming icy mantles. These ice coatings make up about 11% of the total dust mass, and they're composed of familiar molecules. Water ice is the most abundant. But you also find carbon monoxide, carbon dioxide, methanol, ammonia, and even more complex organics. These icy mantles turn dust grains into tiny chemical laboratories. On the surfaces of grains protected from radiation and brought close together by the ice atoms and molecules can react to form new compounds. Hydrogen atoms can combine to form molecular hydrogen, the most abundant molecule in the universe. Simple molecules can link together to form more complex ones. Some of the organic molecules detected in meteorites and comets likely formed this way through surface chemistry on ice-coated dust grains drifting through molecular clouds. So, how do we know all this? How can astronomers be so confident about the composition of dust grains they've never touched? The answer lies in a combination of techniques, each one providing a piece of the puzzle. First, there's spectroscopy, which we've already discussed. By analyzing the wavelengths of light absorbed or emitted by dust, astronomers can identify the minerals and molecules present. Different telescopes observe different wavelengths. Infrared telescopes like Spitzer and Herschel, now retired, mapped the infrared sky with exquisite detail, while the James Webb Space Telescope continues this work with even greater sensitivity. Ground-based radio telescopes detect molecular emission lines from the gases associated with dust. But spectroscopy has limitations. It can tell you what's there, but it doesn't always tell you the exact structure or form. That's where laboratory work comes in. Scientists recreate the conditions of space in vacuum chambers, cooling samples to cryogenic temperatures, and exposing them to ultraviolet radiation. They make synthetic dust grains from various minerals and measure their spectra, creating libraries of spectral signatures that can be compared to astronomical observations. This experimental astrophysics has been crucial for interpreting what we see in space. And then there's the most direct method of all, actually collecting cosmic dust and analyzing it in the laboratory. This isn't science fiction, it's been done, and the results have been revolutionary. Cosmic dust reaches Earth all the time. Every day, tens of thousands of micrometeorites, tiny grains of cosmic dust, drift down through our atmosphere and settle on the surface. Most are so small they don't even heat up significantly during atmospheric entry. They just float down carried by air currents, eventually landing on rooftops in oceans and polar ice. Scientists have developed techniques to collect these particles using high-altitude aircraft to scoop them from the stratosphere, or extracting them from Antarctic ice cores, where they accumulate over millennia. When these particles are examined under electron microscopes and analyzed with mass spectrometers, they reveal astonishing details. Some grains are pristine silicates, glassy spheres formed in the atmospheres of AGB stars. Others are fluffy aggregates, clusters of smaller grains stuck together, preserving the structure they had in the solar nebula 4.5 billion years ago. And some, the rarest and most precious, are pre-solar grains dust that formed around other stars before our sun even existed. Pre-solar grains are identified by their isotopic compositions. Isotopes are variants of elements with different numbers of neutrons. Different stars produce different ratios of isotopes depending on their mass, temperature, and evolutionary stage. When scientists find grains with isotopic ratios dramatically different from solar system values, they know those grains came from another star, a red giant, a supernova, perhaps a star that died billions of years ago. One of the most famous examples came from the Murchison meteorite, which fell in Australia in 1969. Within this meteorite, researchers found tiny grains of silicon carbide with isotopic signatures that could only have come from carbon stars, AGB stars, with more carbon than oxygen in their atmospheres. Some of these grains are more than 7 billion years old, older than the solar system itself, older than the sun. They are quite literally pieces of stars that no longer exist, preserved in a rock that fell from the sky. Think about that for a moment. You can hold in your hand, well, a scientist in a clean room can hold in their hand a grain of dust that was forged inside a star that died before our sun was born, traveled through space for billions of years, got incorporated into the cloud that formed our solar system, survived the formation of asteroids and planets, and finally made its way to Earth inside a meteorite. It's a cosmic journey spanning galaxies and epochs, all contained in a speck of material smaller than a bacterium. But there's more. In 2006, NASA's Stardust mission returned samples from Comet Wild, two collected during a close flyby in 2004. These samples contain not just typical solar system materials, but also pre-solar grains and organic compounds, evidence that comets preserve some of the most primitive, unaltered material from the birth of the solar system. Among the findings were complex organic molecules, including amino acids, the building blocks of proteins. The chemical diversity of cosmic dust is staggering. It's not just rocks and ice. It's a complex mixture of minerals, metals, organic molecules, and ices, each component telling a story about stellar evolution, nucleosynthesis, and the cycling of matter through the universe. And this diversity is essential. Without it, planets couldn't form with the variety of compositions we observe. Earth wouldn't have its iron core, rocky mantle, and water oceans. Life, which requires a delicate balance of elements and molecules, might never have emerged. There's a common misconception that cosmic dust is just one thing, a uniform material like the dust bunnies under your bed. But cosmic dust is endlessly varied. It's olivine crystals and graphite flakes and PAH molecules and water ice. It's pre-solar silicon carbide, older than the sun, and freshly formed silicates from recent supernovae. It's the physical embodiment of the universe's chemical evolution, a library of stellar history, written in atomic structures too small to see, but profound enough to build worlds. And here's something to consider. The dust in your own home, the stuff you vacuum and wipe away, isn't entirely terrestrial. A small fraction of it, perhaps 1 part in 10,000, is actually cosmic dust, micrometeorites that drifted down from space and settled on your windowsill. You're cleaning up stardust without even knowing it. But cosmic dust doesn't remain static. Once it's created, once it's scattered into space with its unique chemical signature, it begins a journey. It moves through the galaxy, pushed and pulled by forces we're only beginning to fully understand, traveling from the death of old stars to the birth of new ones. And that journey is what we'll explore next. Imagine a single grain of cosmic dust, freshly condensed in the cooling wind of a dying red giant. It's alone in the darkness, a speck of olivine no bigger than a bacterium drifting away from the star that made it. What happens next? Does it simply float there forever, suspended in the void? No. That grain is about to embark on an epic voyage across the galaxy, pushed by starlight, carried by stellar winds, swept up in shock waves, pulled by gravity. It will travel hundreds or even thousands of light years, crossing spiral arms, diving through molecular clouds until finally, perhaps millions of years later, it settles into a new nebula where stars are being born. This is the journey of cosmic dust, and it's far more dynamic and violent than you might imagine. If you're enjoying this cosmic voyage, consider liking this video and subscribing to Sleepy Science. It helps us continue exploring the universe together, one gentle story at a time. The first force a newly formed dust grain encounters is the very thing that gave it visibility in the first place: light. Starlight isn't just electromagnetic radiation carrying information across space. It's also a physical force. Photons carry momentum, and when they strike a dust grain, they transfer some of that momentum to the particle pushing it. This is called radiation pressure, and for the smallest dust grains, it's an incredibly powerful force. Here's why radiation pressure matters so much. The force of radiation pressure on a grain depends on its cross-sectional area, essentially how much light it intercepts. But the gravitational pull holding the grain near the star depends on the grain's mass, which scales with volume. For very small grains, the ratio of surface area to volume is large, which means radiation pressure can actually overcome gravity, pushing the grain away from the star despite the star's gravitational pull. Astronomers quantify this with something called the beta ratio, the ratio of radiation pressure force to gravitational force. For grains smaller than about 1/10 of a micrometer, beta can exceed 1, meaning radiation pressure wins. These tiny particles, sometimes called beta meteoroids, are literally blown away from stars by their own light accelerating outward at speeds that can reach hundreds of kilometers per second. This process is happening constantly around every luminous star in the galaxy. The most dramatic examples occur around the hottest, brightest stars, massive O and B-type stars that pour out enormous amounts of ultraviolet radiation. These stars can blow dust grains away so efficiently that they create vast expanding bubbles of hot gas and dust around them, sweeping the interstellar medium clear for dozens of light years in all directions. But radiation pressure is just the beginning. Most stars also produce stellar winds, streams of charged particles flowing outward from their surfaces. Our sun has a solar wind, a thin flow of protons and electrons that extends all the way to the edge of the solar system and beyond. But the stellar winds from evolved stars, red giants, supergiants, and especially AGB stars, are far more powerful. An AGB star can lose mass at rates of 1/millionth to 100 millionth of a solar mass per year through its stellar wind. That might not sound like much, but over tens of thousands of years, it adds up to a significant fraction of the star's total mass. This wind flows outward at speeds of 10 to 30 kilometers per second, and it carries dust grains with it, sweeping them away from the star like leaves in a gale. The interaction between dust and stellar winds is complex and beautiful. As the wind pushes the dust outward, the dust grains absorb some of the star's radiation and re-emit it as infrared light. This radiative heating can actually help drive the wind itself. The dust absorbs momentum from the starlight and transfers it to the gas through collisions, pulling the gas along with it. It's a feedback loop. The wind carries the dust, and the dust helps drive the wind. Astronomers call this a dust-driven wind, and it's one of the key mechanisms by which AGB stars shed their outer layers. But not all dust travels gently. Some dust grains experience the most violent accelerations, imaginable supernova shockwaves. When a massive star explodes as a supernova, it releases more energy in a few seconds than the sun will emit over its entire 10 billion year lifetime. This energy drives a shockwave outward through the star's surrounding material at velocities of 10,000 to 20,000 kilometers per second, a few percent of the speed of light. Any dust grains in the path of this shockwave are subjected to enormous forces. You might think the shockwave would simply vaporize the dust, blasting it back into individual atoms. And indeed, that does happen to some grains, especially the smallest and most fragile ones. But remember what we discussed earlier, supernovae create dust, not just destroy it. The dust that forms in the cooling supernova, ejecta, is actually accelerated by the shock wave carried along with the expanding debris. As this material slams into the surrounding interstellar medium, it creates a complex structure called a supernova remnant, a glowing shell of shocked gas and dust that can remain visible for thousands of years. The Crab Nebula, which we mentioned earlier, is a perfect example. This supernova remnant is expanding at about 1,500 kilometers per second, and infrared observations have detected dust throughout the nebula, both in the fast-moving filaments and in the slower-moving core. This dust is traveling through space at velocities that would carry it from Earth to the Moon in less than 4 minutes. It's a reminder that cosmic dust isn't always the slow, drifting material we might imagine. It can move with incredible speed when driven by extreme events. Now, once dust grains are launched into the interstellar medium, whether gently by stellar winds or violently by supernovae, they don't just coast along in straight lines. They're subject to another fundamental force, gravity. And in a galaxy like the Milky Way, gravity has structure. Our galaxy is a barred spiral, meaning it has a central bar-shaped region and spiral arms winding outward from there. These spiral arms aren't rigid structures like the arms of a pinwheel. They're density waves regions where stars, gas, and dust are temporarily compressed as they orbit the galactic center. Material flows into the spiral arms, slows down, gets compressed, and then flows back out on the other side. It's like a cosmic traffic jam that never quite resolves. Dust grains follow the gravitational pull of these density waves. As they orbit the galaxy, they drift toward the spiral arms where the density of gas and dust is higher. This is where star formation happens most actively, because the compression of material in the spiral arms triggers the collapse of molecular clouds. So, dust grains born around stars in one part of the galaxy eventually make their way into the spiral arms where they can participate in the next cycle of star formation. The timescales involved are staggering. A typical dust grain might take millions of years to journey from the site where it was created to a molecular cloud where it can help form a new star. During that time, it could travel hundreds or thousands of light years, drifting through the diffuse interstellar medium, occasionally passing through denser regions, always subject to the galaxy's gravitational currents. But there's another subtler effect that influences the motion of the dust grains, especially in the context of planetary systems. It's called the Poynting-Robertson effect, and it's both elegant and inexorable. Here's how it works. Imagine a dust grain orbiting a star. The grain absorbs light from the star, which gives it a push in the radial direction away from the star due to radiation pressure. But the grain is also moving in its orbit. So, from the grain's perspective, the starlight appears to be coming slightly from ahead. Due to aberration, the same effect that makes rain appear to slant toward you when you're moving forward in a car. This means the radiation pressure has a component that opposes the grain's orbital motion, acting like a drag force. The grain loses angular momentum and slowly spirals inward toward the star. For very small grains in orbit around a star like the Sun, this inward drift can be quite fast particles. Just a micrometer in size can spiral from the distance of Earth's orbit down to the Sun in less than 1 million years. This Poynting-Robertson drag is one of the main reasons why dusty debris disks around stars eventually clear out over time. Dust grains either grow into larger bodies through collisions, bodies big enough that the drag becomes negligible, or they spiral into the star and are destroyed. It's a natural cleaning mechanism, and it's why older stars tend to have less dust around them than younger stars. The journey of cosmic dust through space is also influenced by magnetic fields. The interstellar medium isn't just gas and dust. It's also threaded with magnetic fields weak by terrestrial standards, but pervasive throughout the galaxy. Charged dust grains and many dust grains pick up a small electric charge from interactions with cosmic rays and ultraviolet light, can be deflected by these magnetic fields, following complex spiraling paths as they drift through space. In some cases, magnetic fields can even trap dust, holding it in place for extended periods. In regions where the magnetic field is particularly strong, such as near young stars, or in certain types of nebulae, dust grains can become aligned with the field lines, all pointing in roughly the same direction. This alignment affects how the dust scatters and polarizes light, and astronomers can use polarization measurements to map out the magnetic field structure in these regions. Let's bring this down to something more tangible. One of the most beautiful and accessible examples of dust being moved by radiation pressure is a comet tail. When a comet approaches the Sun, The ice on its surface begins to sublimate, turning directly from solid to gas without becoming liquid first. This releases dust grains that were frozen into the ice, and these grains are pushed away from the sun by radiation pressure. The result is the comet's dust tail, a graceful curved structure that always points away from the sun, regardless of the comet's direction of motion. If you've ever seen a photograph of a bright comet, you've probably noticed it has two tails, a blue straight ion tail made of charged particles blown by the solar wind, and a yellowish curved dust tail, created by radiation pressure acting on larger grains. The curvature of the dust tail reflects the grain's orbital motion, combined with the outward push of sunlight. It's a visible demonstration of radiation pressure at work, written across the sky in glowing dust. Have you ever wondered why comets have tails in the first place? It's all because of the forces we're discussing: radiation pressure and stellar winds acting on tiny particles released from a ball of ice and rock. And those particles, once freed from the comet, continue their own journeys through the solar system, some of them eventually falling to Earth as micrometeorites. Now, think about the full scope of a dust grain's journey. It begins in the atmosphere of a dying star, or in the debris of a supernova. It's blown outward by radiation, and winds accelerated to speeds of kilometers per second. It drifts through the galaxy for millions of years, crossing vast distances, moving through hot, diffuse gas in some regions, and dense cold clouds in others. It might be irradiated by cosmic rays, sputtered by high-energy particles, coated with icy mantles and molecular clouds. It might collide with other grains, shattering into smaller fragments, or sticking together to form larger aggregates. And eventually, if the grain is fortunate, it ends up in a molecular cloud where gravity is beginning to take hold, where the density is high enough for collapse to occur. There, after its long journey, the dust grain becomes part of something new, a forming star, a protoplanetary disk, perhaps eventually a planet where life might one day emerge. The journey of cosmic dust is not a passive drift. It's an active dynamic process shaped by forces ranging from the quantum pressure of photons to the gravitational architecture of an entire galaxy. And understanding this journey helps us understand how matter cycles through the cosmos, how elements forged in one generation of stars become the raw materials for the next. But the journey is only half the story. What really matters is what happens when dust and light meet, when photons interact with grains scattering, absorbing, transforming, creating some of the most spectacular visual phenomena in the universe. That luminous dance is what we'll turn to next. Light and dust are locked in an eternal dance across the cosmos, partners in one of nature's most beautiful and consequential relationships. When a photon, a particle of light that has traveled unimpeded through the vacuum of space for perhaps thousands of years, finally encounters a grain of cosmic dust, no larger than a smoke particle, something remarkable happens. The photon might be absorbed, its energy converted to heat. It might be scattered, deflected in a new direction, its path forever altered. Or it might pass through untouched, continuing its journey as if nothing had happened. This interplay between light and dust creates some of the most stunning visual phenomena in the universe, from the blue glow of reflection, nebulae, to the dark silhouettes of molecular clouds. But it also poses one of astronomy's greatest challenges. Dust doesn't just reveal the universe to us, it also hides it. If these cosmic interactions fascinate you alike on this video, helps others discover these stories, and subscribing to Sleepy Science ensures you never miss our gentle explorations of the universe. Let's start with a fundamental question. Why does dust affect light at all? Why doesn't light simply pass through dust grains as if they weren't there? The answer lies in the nature of light itself, and in the size and composition of dust grains. Light is both a wave and a particle, a quantum phenomenon that exhibits properties of both depending on how you observe it. When we think about light interacting with dust, it's helpful to think of it as an electromagnetic wave oscillating electric and magnetic fields propagating through space. When this wave encounters a dust grain, the electric field causes the electrons in the grain's atoms to oscillate. These oscillating electrons then re-radiate electromagnetic energy in various directions. The details of how this happens, how much energy is absorbed versus scattered, and in which directions the scattered light goes, depend critically on the relationship between the wavelength of light and the size of the dust grain. This is where things get beautifully complex, because cosmic dust grains come in a range of sizes and different wavelengths of light interact with them in fundamentally different ways. For the smallest dust grains, those much smaller than the wavelength of light, a process called Rayleigh scattering dominates. This is the same scattering that makes Earth's sky blue and sunsets red, but it happens on a cosmic scale. Rayleigh scattering has a strong dependence on shorter wavelengths. Blue and violet light are scattered much more efficiently than longer wavelengths like red and infrared. Specifically, the amount of scattering is inversely proportional to the fourth power of wavelength. This means blue light with a wavelength around 450 nanometers is scattered about 9 times more strongly than red light at 650 nanometers. In space, this creates the ethereal blue reflections nebulae we see around hot young stars. The Pleiades star cluster, also known as the Seven Sisters, is surrounded by a diffuse blue glow, not because the stars themselves are producing blue light exclusively, but because they're embedded in a cloud of dust that preferentially scatters their blue wavelengths toward us, while allowing red wavelengths to pass through or be absorbed. The result is a stunning azure haze like celestial smoke, illuminated by brilliant diamonds. The discovery of why these nebulae appear blue is a story worth telling. In the early 20th century, astronomers like Edwin Hubble, yes, the same Hubble, the Space Telescope is named after studied reflection nebulae, and initially thought they might be glowing due to fluorescence with the dust, somehow absorbing ultraviolet light and re-emitting it at visible wavelengths. But detailed spectroscopic studies showed something different. The spectrum of a reflection nebula is essentially identical to the spectrum of the illuminating star, just shifted toward bluer wavelengths. This was the signature of scattering, not emission. The blue color wasn't being created by the dust, it was being selected from the star's light through preferential scattering of shorter wavelengths. Now, as dust grains get larger, approaching or exceeding the wavelength of light, a different regime takes over, called me-scattering. My scattering is more complex mathematically, but the key point is that it's less wavelength dependent than Rayleigh scattering. Larger grains scatter all wavelengths more equally, which means they produce white or neutral colored reflection rather than blue. This is why clouds in Earth's atmosphere appear white rather than blue. Water droplets in clouds are typically 10 to 20 micrometers across, much larger than the wavelength of visible light. They scatter all wavelengths roughly equally, so cloud light contains all colors mixed together, which our eyes perceive as white. The same principle applies in space nebulae, with larger dust grains can appear whitish or gray in reflected light, lacking the characteristic blue tint of Rayleigh-dominated reflection nebulae. But scattering is only part of the story. Dust grains don't just redirect light, they also absorb it, converting the photon's energy into heat. And this absorption has profound consequences for how we see the universe. When starlight passes through a dusty region, some photons are scattered out of the line of sight and others are absorbed entirely. The combined effect is that the star appears dimmer than it would if the dust weren't there. Astronomers call this interstellar extinction, and it's one of the most important corrections we have to make when measuring the properties of distant stars and galaxies. The amount of extinction depends on both the total amount of dust along the line of sight and the wavelength of light we're observing. In the visible part of the spectrum, extinction is significant, roughly 1 magnitude of dimming per kiloparsec of distance through the dusty disk of the Milky Way. 1 magnitude means the star appears about 2.5 times fainter than it actually is. If you're looking at a star 10 kiloparsecs away, about 33,000 light years, roughly the distance from Earth to the galactic center, extinction could make it appear 2,500 times fainter than it truly is. That's the difference between a star you can easily see with binoculars and one you can't detect at all without a powerful telescope. Even more importantly, dust doesn't just dim light, it reddens it. Because dust scatters and absorbs blue light more efficiently than red light, distant stars viewed through dust appear redder than they actually are. This is called interstellar reddening, and if you don't account for it, you can badly misjudge a star's temperature, its luminosity, and its distance. The history of astronomy is filled with errors caused by not properly accounting for dust. One of the most famous examples involves Jacobus Kapteyn, a Dutch astronomer working in the early 1900s. Kapteyn conducted extensive surveys of star positions and brightnesses, trying to map the structure of the Milky Way. Based on his observations, he concluded that the Sun was near the center of a relatively small galaxy, only about 15 kiloparsecs across. Kapteyn was wrong, but not because his observations were bad. He was wrong because he didn't fully account for interstellar extinction. The dust in the galactic plane was blocking his view of distant stars, making it seem like the density of stars dropped off rapidly with distance. He was seeing the edges of his observable universe, not the true edges of the galaxy. The Milky Way is actually much larger, about 30 kiloparsecs in diameter, and the Sun is far from the center, about 8 kiloparsecs out in the disk. It took the work of Harlow Shapley studying globular clusters in 1918 to reveal the truth. Shapley realized that the globular clusters were distributed in a spherical halo around a point far from the Sun, the true center of the galaxy. And he recognized that interstellar extinction was dimming stars and making the galaxy appear smaller than it was. This was a pivotal moment in astronomy, the realization that our view of the universe was being systematically distorted by cosmic dust. Even today, extinction remains a challenge. When astronomers observe distant galaxies, they have to carefully model how much dust lies between us and them both in our own galaxy and in the distant galaxy itself to accurately measure properties like luminosity and star formation rates. It's a subtle, complex problem requiring detailed understanding of dust properties and distributions. But here's where it gets truly fascinating. Dust doesn't just absorb light and discard the energy. It re-radiates that energy, but at different wavelengths. When a dust grain absorbs a high-energy ultraviolet or visible photon, it heats up slightly. To stay in thermal equilibrium, it must radiate away that energy, and it does so primarily in the infrared. This process transforms the universe. Hot young stars emit most of their energy at ultraviolet and visible wavelengths. But if they're embedded in dusty regions, much of that radiation is absorbed by dust and re-emitted at infrared wavelengths. The result is that dusty star-forming regions, which would be relatively dim in visible light, become incredibly bright in the infrared. Entire galaxies undergoing vigorous star formation can emit more than 90% of their total energy output in the infrared, simply because so much of their starlight is being processed through dust. This realization revolutionized astronomy in the late 20th century, when infrared satellites like IRAS, the Infrared Astronomical Satellite launched in 1983, began surveying the sky. They revealed a universe that looked completely different from the one we see in visible light. Dusty star-forming regions glowed brilliantly. The galactic plane, dark and obscured in visible light, blazed with infrared emission from warm dust. And distant galaxies, invisible optically due to dust, suddenly became detectable as bright infrared sources. The Spitzer Space Telescope, launched in 2003, and the Herschel Space Observatory, operational from 2009 to 2013, continued this exploration with even greater sensitivity and resolution. They mapped the distribution of dust throughout the Milky Way, traced the formation of stars inside opaque molecular clouds, and studied the evolution of dusty galaxies across cosmic time. And now, the James Webb Space Telescope, with its powerful infrared capabilities, is revealing dust and star formation in unprecedented detail, peering through cosmic dust. to see the universe in ways previous generations of astronomers could only dream of. Let's make this concrete with one of the most iconic images in all of astronomy, the Horsehead Nebula. Located in the constellation Orion, the Horsehead is a dark nebula, a dense cloud of gas and dust silhouetted against a background of glowing hydrogen gas. In visible light images, it appears as a striking black shape, like the head and neck of a horse emerging from a foggy landscape. The darkness isn't absence, it's dust thick enough to block virtually all visible light from the bright emission nebula behind it. But point an infrared telescope at the Horsehead, and the scene transforms. Suddenly, you can see through the dust. The nebula becomes semi-transparent, revealing young stars forming inside, hidden from visible wavelengths, but glowing in the infrared. The dust itself, heated by nearby stars, glows warmly, outlining the structure of the cloud. What was opaque becomes translucent. What was hidden becomes visible. This is the power of observing at different wavelengths. Dust that blocks visible light is often transparent to infrared and radio waves. By combining observations across the electromagnetic spectrum, astronomers can build a complete picture of dusty regions. How much dust is there, how it's distributed, what temperatures it has, and what's happening inside the clouds. Think about the irony here. Dust is both astronomy's greatest obstacle and one of its most valuable tools. It obscures our view of the universe in some wavelengths, forcing us to develop new technologies and techniques to see through it. But it also reveals processes we couldn't observe, otherwise glowing in the infrared, to trace star formation, scattering light, to create beautiful nebulae, and blocking background light to reveal the structure of dark clouds. There's a specific region of the Milky Way that perfectly illustrates this dual nature of dust, the zone of avoidance. This is a band around the galactic plane where our view of the distant universe is severely obscured by dust in our own galaxy. When astronomers map the distribution of galaxies across the sky, they find an empty band not because galaxies don't exist in those directions, but because the dust in the Milky Way's disk blocks our view of them. For decades, this zone of avoidance was a blind spot in extragalactic astronomy. We simply couldn't see what lay behind the dust. But with infrared and radio telescopes, astronomers have begun to peer through the veil, discovering previously unknown galaxies and clusters hidden in plain sight, masked by cosmic dust. Perhaps the most visually stunning demonstration of dust's interaction with light is the Great Rift, also called the Dark Rift, a series of overlapping dark clouds that appears to divide the Milky Way in two when you view it from a dark sky location on a summer night. This dark lane stretches from the constellation Cygnus down through Aquila and Sagittarius, creating a shadowy river through the center of the galactic band. Ancient cultures saw this dark region and incorporated it into their mythologies. The Inca of South America called it the Mayu, the celestial river. They recognized shapes in the darkness, a llama, a fox, a toad, just as we recognize shapes in the bright constellations. They understood intuitively that this darkness was something real, something present, not merely the absence of stars. They were right. The Great Rift is a complex of molecular clouds in the local spiral arm of the Milky Way, filled with dense gas and dust. It's opaque and visible light, blocking our view of the billions of stars beyond. But it's also a nursery, a region where new stars are actively forming, hidden from our eyes, but detectable with infrared instruments. When you understand what dust does to light, how it scatters, absorbs, reddens, and re-radiates, you begin to see the night sky differently. Those dark patches aren't empty. They're full of potential, pregnant with the raw materials for future stars and planets. The dimming and reddening of distant stars isn't a nuisance, it's a message telling us about the dust between here and there, its quantity and composition. But dust's most profound role isn't in how it affects light we observe from afar. It's in what it enables here in the cold, dark clouds, where gravity is pulling matter together and stars are beginning to form. There, dust becomes not just an observer of light, but an active participant in creation itself. In the coldest, darkest corners of the galaxy, where temperatures plunge to just 10 degrees above absolute zero, and light from distant stars barely penetrates, something miraculous is happening. Inside, vast molecular clouds spanning hundreds of light years, gravity is winning its patient battle against pressure and turbulence. Gas is collapsing, condensing, heating up. And at the heart of this cosmic drama, playing a role so essential that without it, stars might never form, at all, is dust. Those same microscopic grains we've been following, scattered by dying stars, journeying across the galaxy, hiding and revealing the universe, now become the architects of creation itself. Cosmic dust doesn't just passively witness the birth of stars. It enables it, facilitates it, makes it possible. And the way it does this is one of the most elegant solutions in all of nature. If the story of how dust builds stars resonates with you, like helps this video reach more curious minds, and subscribing means you'll continue this journey with us through the cosmos. To understand why dust is so critical for star formation, we need to appreciate a fundamental problem that molecular clouds face. These clouds are immense. Some contain enough material to make hundreds of thousands of stars like the Sun. They're composed primarily of molecular hydrogen, with a sprinkling of heavier molecules like carbon monoxide, water, ammonia, and formaldehyde. And crucially, they're cold, with temperatures typically between 10 and 50 Kelvin. This coldness is essential because cold gas has low pressure. And low pressure means gravity can overcome the gas's resistance to collapse. But here's the problem. As a cloud begins to collapse under its own gravity, it heats up. This is basic physics. When you compress a gas, you do work on it, and that work converts to thermal energy. The temperature rises. And if the temperature rises too much, the pressure increases enough to halt the collapse entirely. The cloud reaches a state of equilibrium, balance between gravity pulling inward and pressure pushing outward, and star formation stalls. For stars to form, the cloud needs a way to shed that gravitational energy, to radiate it away into space so the collapse can continue. In the hot ionized gas that makes up much of the universe, this is relatively easy. Charged particles can radiate energy efficiently through various atomic and molecular processes. But in the cold neutral molecular hydrogen that dominates these clouds, radiating energy is difficult. Molecular hydrogen is a poor radiator at low temperatures. It simply doesn't have the right energy level transitions to efficiently emit the heat generated by gravitational collapse. This is where dust saves the day. Dust grains are excellent radiators, especially at infrared wavelengths. When gas molecules collide with dust grains, they can transfer their kinetic energy, their heat, to the grain. The grain in turn radiates this energy away as infrared photons, which can escape from the cloud and carry the energy into space. This process cools the gas, allowing it to continue collapsing. Without dust, molecular clouds would be much warmer, and star formation would be far less efficient, perhaps impossible in many regions. Think of dust as the galaxy's cooling system, a cosmic thermostat that allows clouds to stay cold enough for gravity to sculpt them into stars. The amount of dust doesn't need to be large. Remember, dust makes up only about 1% of the mass of the interstellar medium, but its influence is disproportionate to its abundance. That 1% makes the difference between a static cloud and a stellar nursery. But dust's role goes beyond just cooling. It also serves as the surface upon which some of the most important chemical reactions in the universe take place. In the frigid environment of a molecular cloud, atoms and molecules move slowly, and many reactions that would happen readily at higher temperatures simply don't occur in the gas phase. But on the surface of a dust grain, chemistry comes alive. The most crucial reaction is the formation of molecular hydrogen itself. Molecular hydrogen H2 is the most abundant molecule in the universe, making up the bulk of the material in molecular clouds. Yet, it's surprisingly difficult to form in empty space. Two hydrogen atoms can't simply collide and stick together to form H2. When they try, the newly formed molecule has too much energy, it's in an excited state. And unless that energy can be carried away immediately, the molecule simply breaks apart again. In the gas phase, there's no efficient way to remove that excess energy quickly enough. But on a dust grain surface, the process works beautifully. A hydrogen atom drifts through space and lands on a grain sticking to the surface. Later, another hydrogen atom lands nearby. The two atoms can migrate across the grain surface, hopping from site to site until they meet and bond, forming H2. The dust grain absorbs the excess energy from the reaction, acting as a third body that stabilizes the molecule. The newly formed H2 then evaporates from the surface and joins the gas. Without dust grains providing these catalytic surfaces, molecular clouds wouldn't have enough H2 to collapse and form stars. The entire process of star formation depends on this surface chemistry happening on grains smaller than bacteria. Scientists discovered this through painstaking laboratory experiments in the 1960s and 70s. Researchers created vacuum chambers cooled to cryogenic temperatures, coated surfaces with materials mimicking cosmic dust, and exposed them to atomic hydrogen. They watched as H2 formed efficiently on these surfaces, confirming what theorists had predicted. It was a beautiful validation of the idea that dust isn't just debris, it's a factory, a substrate for the chemistry that builds the universe. Now, let's follow what happens. As a molecular cloud cooled by dust and enriched with H2 formed on dust, grain surfaces begins to collapse. The process doesn't happen all at once. Molecular clouds are turbulent with supersonic flows and chaotic motions, creating regions of varying density. The densest regions where perhaps a shock wave from a nearby supernova has compressed the gas, or where turbulent flows have collided, are where collapse begins first. These dense cores fragment further as they collapse, breaking into smaller and smaller clumps. Eventually, you get protostellar cores regions a few thousand astronomical units across where a single star or a multiple star system will form. At the center of such a core, the density becomes high enough that the gas becomes opaque to its own radiation. The core can no longer cool efficiently by radiating energy away. The temperature begins to rise more rapidly, and a hydrostatic core forms a central object in pressure equilibrium. Not yet a true star, but the seed from which a star will grow. Surrounding this central protostar is a disk of material, a protoplanetary disk, sometimes called a circumstellar disk or accretion disk. This disk forms because the collapsing cloud has some initial rotation, and as material falls inward, conservation of angular momentum forces it to spin faster and flatten into a disk, much like a spinning pizza dough flattens as you toss it in the air. And this disk, this is where planets are born. And dust is the key. In the early days of studying planet formation, astronomers faced a significant puzzle. The Standard Model developed in the mid-20th century by scientists like Viktor Safronov proposed that planets form through the gradual accumulation of solid material in the protoplanetary disk. Dust grains collide and stick together, growing into larger aggregates. These aggregates collide and merge, becoming pebbles, then boulders, then kilometer-sized objects called planetesimals. Planetesimals gravitationally attract more material, growing into protoplanets and eventually into full-size planets. It's an elegant picture, but there's a problem: the meter-sized barrier. Computer simulations showed that once particles grow to about a meter in size, they face a catastrophic problem. They're large enough that gas drag from the protoplanetary disk becomes significant, but not large enough that gravity can hold them together against the shear forces they experience. The drag causes them to spiral inward toward the star incredibly quickly. Within just a few hundred orbits, they could be swallowed by the central star. At the same time, when these meter-sized objects collide with each other at the high velocities typical of protoplanetary disks, they tend to shatter rather than stick together. For years, this was a major unsolved problem. How do you get from millimeter-sized dust grains to kilometer-sized planetesimals without getting stuck at the meter-sized barrier? How did Earth and Mars and Jupiter and all the planets we see around other stars ever manage to form? The answer, astronomers now believe, involves several clever mechanisms, many of which directly involve dust. One key insight came from studying the properties of dust grain collisions in more detail. It turns out that under the right conditions, low relative velocities, fluffy grain structures, the presence of icy coatings grains can stick together quite effectively. Laboratory experiments have shown that ice-coated grains in particular can collide at velocities of tens of meters per second and still stick, whereas bare silicate grains shatter at much lower speeds. This means that in the outer parts of protoplanetary disks beyond what's called the snow line, the distance from the star, where temperatures are cold enough for water to condense, as ice grain growth can proceed much more rapidly. Ice mantles make grains stickier, and because water is abundant, icy grains grow faster, accumulating more mass. This is one reason why the giant planets in our solar system, Jupiter, Saturn, Uranus, Neptune, all formed in the outer system where ice could exist. Another key mechanism involves the concentration of dust in certain regions of the disk. Turbulence, magnetic fields, and pressure variations can create local zones where dust particles drift inward, pile up, and reach high enough densities that gravity becomes significant even for small objects. These dust traps can allow particles to skip the meter-sized barrier, entirely going directly from small pebbles to planetesimals through a process called gravitational collapse of the dust layer. When the dust density gets high enough, the layer becomes gravitationally unstable and fragments into clumps, instant planetesimals, born from the collective collapse of countless dust grains. We can actually see this process happening in real time, well, not quite real time, but in systems young enough that planet formation is still ongoing. In 2014, the Atacama Large Millimeter Array, or ALMA, released an image that stunned the astronomical community. It showed a young star called HL Tauri, located about 450 light-years from Earth, surrounded by a protoplanetary disk with exquisite detail. The disk wasn't smooth. It showed a series of bright rings and dark gaps, concentric circles etched into the dust distribution like grooves in a vinyl record. These gaps are almost certainly carved by young planets embedded in the disk. As a planet orbits, its gravity sweeps up material along its orbital path, creating a gap in the dust and gas. The bright rings between the gaps are where dust accumulates piled up by the gravitational influence of the planets. The HL Tauri image was a direct visual confirmation of planet formation in action, showing dust being sculpted by gravity into the structures that will eventually become a planetary system. And here's what's remarkable. HL Tauri is less than 1 million years old. Planet formation is happening far faster than early models predicted. The dust in the disk is clumping, coalescing, growing at rates that suggest terrestrial planets could form in just a few million years, and gas giants potentially even faster. Since HL Tauri ALMA and other telescopes have imaged dozens of protoplanetary disks, revealing an astonishing diversity of structures. Some disks have multiple gaps suggesting multiple planets. Others have spiral patterns, possibly driven by gravitational instabilities or interactions with massive planets. Still others show asymmetric clumps, crescents of dust piled up in arcs around the star. Each structure tells a story about the dynamics of planet formation, about how dust is being moved and concentrated by gravity pressure and magnetic fields. Have you ever wondered why planets in our solar system have such different compositions? Why Earth is rocky while Jupiter is gaseous? Why Mars is small while Saturn has magnificent rings? The answer lies in where they formed in the protoplanetary disk and how dust behaved at those different distances from the Sun. The inner system, hot and dry, had only silicate and metallic dust. The outer system beyond the snow line had all that, plus abundant water ice and other frozen volatiles. These differences in available dust shaped the planets that formed. But Let's return to the broader picture of star formation, because while we've been focusing on the disk and planet formation, the star itself is still growing. Material from the surrounding cloud continues to fall onto the disk, and from the disk onto the central protostar. Over a few 100,000 years, the protostar accumulates enough mass that its core temperature rises to about 10 million Kelvin, hot enough for hydrogen fusion to begin. At that moment, the protostar becomes a true star, generating its own energy through nuclear reactions, no longer dependent on gravitational contraction for its luminosity. This newborn star is often still surrounded by its protoplanetary disk, and may be embedded in a cocoon of remaining dust and gas from the original molecular cloud. But the star's radiation and stellar wind begin to clear away this material. Ultraviolet photons from the hot stellar surface ionize the surrounding gas, creating an H2 region, a bubble of ionized hydrogen that expands outward. Stellar winds push dust and gas away from the system. Over a few million years, the natal cloud is dispersed, revealing the star and its forming planetary system to the universe. And throughout this entire process, from the initial collapse of the cloud to the clearing of the natal material, dust has been indispensable. It cooled the gas, it catalyzed the formation of molecules, it provided the raw material for planets, it absorbed stellar radiation and re-emitted it as infrared, regulating the thermal structure of the disk. Without dust, none of this works. The universe would be a very different place. Fewer stars, no rocky planets, perhaps no life. The story of star formation is often told as a story of gravity and gas, but it's equally a story of dust. Those microscopic grains forged in dying stars and scattered across the galaxy find their way into cold molecular clouds and become the seeds of new stellar generations. They are the link between death and rebirth, the material continuity that connects each generation of stars to the next. Yet the dust's creative work doesn't end when stars and planets form. In fact, in one particular planetary system, ours dust has left traces and clues that we can study up close, revealing details about the solar system's formation that we could never learn from distant observations alone. And that nearby perspective is where our exploration takes us next. Every clear night, about an hour and a half before sunrise, if you're in a place far from city lights and you look toward the eastern horizon, you might see something subtle and beautiful, a faint wedge-shaped glow rising up from where the sun will soon appear. It's soft, ghostly, easily mistaken for the first hints of dawn. Ancient Persian astronomers called it the false dawn. Modern astronomers call it the zodiacal light. And what you're seeing stretched across millions of miles of space is sunlight reflecting off cosmic dust. Not dust between distant stars, but dust right here in our solar system, orbiting the sun alongside the planets. A glowing reminder that we live inside a dusty cosmic neighborhood. If these close-to-home cosmic wonders intrigue you, A-Like helps share this journey with others. And subscribing to Sleepy Science means you'll never miss our explorations of the universe, told softly, one story at a time. The solar system is far from empty. Between the orbits of the planets, filling the space from Mercury out past Neptune, floats a thin haze of dust particles. These aren't the primordial grains from the solar nebula that formed 4.5 billion years ago. Most of that original dust was either swept up into planets and asteroids during formation, or blown out of the system by the young sun's intense radiation and stellar wind. Instead, the dust we see today is being continuously replenished by two main sources: collisions between asteroids and the asteroid belt, and the shedding of material from comets as they pass near the sun. Let's start with the asteroid contribution, which accounts for roughly 85% of the interplanetary dust particles, or IDPs, in the inner solar system. The asteroid belt, located primarily between Mars and Jupiter, contains millions of rocky bodies ranging from Ceres nearly 1,000 kilometers across down to pebbles and boulders. These asteroids are the leftover building blocks of planet formation and fragments that, never quite managed to accrete into a planet kept stirred up and prevented from coalescing by Jupiter's powerful gravitational influence. Asteroids don't orbit in perfect isolation. They collide. Over billions of years, these collisions have ground down larger asteroids into smaller fragments, creating a cascade of debris. When two asteroids smash into each other at velocities of several kilometers per second, the impact shatters both bodies, creating countless fragments. The largest pieces remain as smaller asteroids. The smallest dust grains, ranging from micrometers to millimeters in size, are released into orbit around the Sun. This dust doesn't remain in the asteroid belt. The same forces we discussed earlier, radiation pressure, Poynting Robertson drag, and gravitational perturbations from the planets cause these particles to migrate inward toward the Sun, or outward toward the outer solar system. Some grains spiral into the Sun and are vaporized. Others are ejected from the solar system entirely when they pass close to a planet and receive a gravitational boost. But at any given time, there's a steady-state population of dust orbiting throughout the inner solar system, constantly being replenished by new collisions as old particles are removed. The other 15% of interplanetary dust comes from comets, and this contribution, though smaller in total mass, is extremely important for understanding the composition and history of the solar system. Comets are icy bodies often described as dirty snowballs, though that undersells their complexity that formed in the cold outer regions of the solar nebula. Most comets spend the majority of their time far from the Sun in two main reservoirs, the Kuiper Belt beyond Neptune and the even more distant Oort cloud, a spherical shell of icy bodies extending perhaps halfway to the nearest star. When a comet's orbit brings it close to the Sun, solar heating causes the ice on its surface to sublimate, releasing gas and dust that were frozen into the ice. This creates the comet's distinctive coma, a glowing atmosphere of gas and dust, surrounding the solid nucleus and its tails, which we've already mentioned in the context of radiation pressure. As the comet passes through the inner solar system, it sheds dust continuously, leaving behind a trail of particles along its orbital path. These cometary dust trails are remarkable structures. They persist for decades or even centuries after the comet has moved on, creating streams of particles that orbit the Sun along the same path the comet took. And here's something wonderful: when Earth's orbit intersects one of these dust streams, we get a meteor shower. The dust particles enter Earth's atmosphere at high velocities, typically between 10 and 70 kilometers per second, and burn up due to friction with the air, creating the bright streaks we call meteors or shooting stars. Different meteor showers are associated with different comets. The Perseids, one of the most reliable and spectacular annual meteor showers, occur when Earth passes through the dust trail left by Comet Swift-Tuttle. The Leonids come from Comet Tempel-Tuttle. The Geminids, interestingly, are associated with an object called 3200 Phaethon, which is technically classified as an asteroid, but behaves more like an extinct comet, a rocky remnant of a comet that has lost most or all of its volatile ices. When you watch a meteor shower, you're seeing cosmic dust individual grains, most no larger than a grain of sand, meeting their end in a brief, brilliant flash. It's a visceral reminder that space isn't empty, that Earth is constantly moving through a sea of particles, that we're part of a dynamic system where dust is everywhere. But most interplanetary dust doesn't burn up dramatically in meteor showers. It falls to Earth quietly and visibly all the time. Estimates suggest that about 40,000 tons of extraterrestrial material falls to Earth each year. Some of this is in the form of larger meteorites, chunks of asteroids, or rarely pieces of the Moon or Mars knocked into space by impacts. But the vast majority is dust, tiny particles decelerated by the upper atmosphere, drifting down so gently they never heat up enough to glow, eventually settling on the surface. This cosmic dust is literally everywhere on Earth. It's in the soil, in the oceans, in polar ice cores, on rooftops. Most of it is indistinguishable from terrestrial dust unless you examine it very carefully. But some particles have distinctive features, unusual chemical compositions, preserved glassy textures from space, weathering sometimes even pre-solar grains embedded within them that mark them as extraterrestrial. Scientists have developed clever ways to collect these particles. In the 1970s, NASA began using high-altitude research aircraft, specially modified U-2 spy planes flying at altitudes above 60,000 feet, to scoop cosmic dust from the stratosphere. At those altitudes above most of Earth's weather and dust, the concentration of extraterrestrial particles is higher and easier to distinguish from terrestrial contamination. The collected particles, typically 10 to 100 micrometers across, are brought back to laboratories for detailed analysis. What researchers found astonished them. These interplanetary dust particles are incredibly diverse, ranging from compact glassy spherules, formed when particles heated up during atmospheric entry, to fluffy, delicate aggregates that look like microscopic tumbleweeds, clusters of even smaller grains loosely stuck together. Some particles are pure silicates. Others contain organic compounds, complex carbon-based molecules that survive the journey through space and the entry into Earth's atmosphere. And a few rare particles contain pre-solar grains, the same ancient stardust we discussed earlier, older than the solar system itself. One of the most scientifically valuable collections of cosmic dust comes from an unlikely place, Antarctic ice. Antarctica is one of the best places on Earth to find meteorites because they're easy to spot against the white ice, and because the ice preserves them well. But micrometeorites, tiny particles of cosmic dust, are even more abundant. At certain locations in Antarctica, where ancient ice layers are exposed and slowly ablate away due to wind erosion, micrometeorites accumulate in concentrated patches. Scientists can collect thousands of particles from just a few kilograms of ice. These Antarctic micrometeorites have provided crucial insights into the composition and diversity of interplanetary dust. Because they're collected from ice of different ages, scientists can even study how the flux of cosmic dust has changed over time, looking for variations that might correlate with events in the solar system's history. But perhaps the most ambitious effort to study interplanetary dust came not from collecting particles on Earth, but from going out into space to meet them. In 1999, NASA launched the Stardust mission, a spacecraft designed to fly through the coma of Comet Wild 2 and collect dust particles, then return them to Earth for analysis. The engineering challenges were immense. The spacecraft would be traveling at 6 kilometers per second, relative to the comet and dust grains. At that velocity hit, with tremendous force, a particle the size of a grain of sand carries the kinetic energy of a bowling ball dropped from a tall building. To capture the particles without destroying them, scientists developed a remarkable material called aerogel, an ultra-low-density silicon-based foam that's 99.8% air. Aerogel is so light that it seems almost ghostly, and it can gently decelerate hypervelocity particles, slowing them down without vaporizing them. In January 2004, Stardust flew within 236 kilometers of Comet Wild 2's nucleus, passing through the inner coma and collecting thousands of particles in its aerogel collector. The encounter lasted just minutes, but it was a complete success. 2 years later, in January 2006, the sample return capsule re-entered Earth's atmosphere and parachuted down to a landing in the Utah desert. It was the first time cometary material had been brought back to Earth for laboratory study. The analysis of stardust samples revealed surprises. Scientists expected to find mostly primitive, unaltered material, icy grains, and organic compounds that had never been heated or processed since the formation of the solar system. And they did find that. But they also found something unexpected: high-temperature minerals, including particles of olivine and calcium aluminum-rich inclusions, similar to those found in meteorites, materials that must have formed in the hot inner solar nebula near the Sun. What were these high-temperature minerals doing in a comet that formed in the cold outer solar system? The answer tells us something profound about the early solar system's dynamics. The solar nebula wasn't a static disk with hot material near the sun and cold material far away. It was dynamic, turbulent, with powerful flows that could transport material over vast distances. Some of the dust that formed near the sun was carried outward, mixed into the cold outer regions, and incorporated into comets. Comets, then, are not purely primitive outer solar system objects. They're mixtures, blends of material from different parts of the solar nebula, cosmic archives that preserve both the hottest and coldest environments of the young solar system. Among the stardust samples, researchers also found pre-solar grains, 7 of them in fact, tiny particles of silicon carbide and graphite with isotopic signatures proving they formed around other stars before the solar system existed. These grains are more than 7 billion years old, making them among the oldest solid materials ever studied in a laboratory. They survived the collapse of the molecular cloud that formed the sun, the formation of the solar nebula, the accretion of comets in the outer solar system, and the journey through space to Comet Wild 2. And then they survived collection by stardust and analysis on Earth. Think about the journey of one of those grains. It condensed in the wind of a red giant star 7 billion years ago, perhaps in a galaxy far from the Milky Way. It drifted through interstellar space for billions of years, eventually making its way to the molecular cloud that would become our solar system. It was incorporated into a comet 4.5 billion years ago and spent the next 4.5 billion years frozen in ice orbiting the sun in the dark outer reaches of the solar system. Then in 2004, it was captured by a spacecraft and brought to Earth, where scientists used mass spectrometers and electron microscopes to read its atomic secrets. It's a journey beyond imagination, spanning galaxies and epochs, connecting us to stellar processes that happened before our sun was born. And it's all contained in a speck of material so small you'd need a powerful microscope to see it. But Stardust wasn't the only mission to collect extraterrestrial samples. Japan's Hayabusa mission returned samples from asteroid Itokawa in 2010, and its successor Hayabusa 2 brought back material from asteroid Ryugu in 2020. NASA's OSIRIS-REx mission returned samples from asteroid Bennu in 2023. Each of these missions has provided unprecedented insights into the composition and history of small bodies in the solar system. And in every case, dust, tiny particles of silicates, organics, and sometimes ice has been at the heart of the discoveries. The picture that emerges from all this research, from meteorites, from Antarctic micrometeorites, from collected stratospheric dust, from returned comet and asteroid samples, is one of astonishing diversity and complexity. The solar system's dust isn't a single uniform material. It's a mixture of different sources, different compositions, different ages. It includes fresh dust from recent asteroid collisions, ancient grains from the solar nebula, pre-solar stardust from other stars, and cometary particles enriched with organic molecules. And here's something to consider right now. As you sit here listening to this, cosmic dust is falling all around you. Every day, dozens of tons of interplanetary dust particles drift down through the atmosphere and settle on the surface. Some land in oceans where they sink to the seafloor and become part of marine sediments. Others land on continents where they mix with terrestrial soil. A few might land on your roof, your car, your windowsill. You're living in a gentle, invisible rain of stardust, a continuous delivery of extraterrestrial material that connects Earth to the broader solar system. Have you ever thought about the fact that the dust you clean from your home includes particles from space? It's a humbling and beautiful realization. The boundary between Earth and space is more porous, more permeable than we often imagine. Yet, for all the wonder and insight that studying solar system dust has provided, it has also revealed a persistent challenge. One that affects everything from astronomical observations to spacecraft operations to understanding the history of our cosmic neighborhood. Dust, as essential and fascinating as it is, also obscures, interferes, and sometimes frustrates our attempts to see clearly. And that paradox is what we'll explore as we continue. There's a direction in space where our view of the universe simply ends. Not because space itself ends there, not because galaxies cease to exist beyond that boundary, but because something stands in the way, blocking our sight as effectively as a wall blocks your view of what's on the other side. That obstacle is dust, vast lanes of it, clouds of it, concentrated along the plane of our galaxy so thickly that visible light simply cannot penetrate. Astronomers have a name for this cosmic blind spot, the zone of avoidance. And for more than a century, this dusty veil has been both a scientific frustration and a profound reminder that the universe we see is not the universe as it truly is, but merely the universe as dust allows us to see it. If the hidden universe intrigues you, your like helps us illuminate these cosmic mysteries for others, and subscribing ensures you're part of every discovery we share on Sleepy Science. The zone of avoidance is a band roughly 20 degrees wide, centered on the plane of the Milky Way, where our observations of distant galaxies become severely compromised or impossible. When astronomers create maps of galaxy distributions across the sky, they see galaxies everywhere above the galactic plane, below it in every direction, except for this conspicuous gap, this river of emptiness cutting across their surveys. It looks as if the universe is somehow depleted in that region, as if galaxies avoid forming near our galaxy's equator. But that's an illusion. The galaxies are there. We just can't see them. The dust in the Milky Way's disk, concentrated in the spiral arms and in dense molecular clouds, absorbs and scatters the light from background galaxies so thoroughly that they become invisible in optical wavelengths. It's like trying to see distant mountains through a thick fog, no matter how bright the mountains are. If the fog is dense enough, you simply can't see through it. This wasn't always understood. In the early 20th century, when astronomers first began systematically cataloging galaxies, they noticed this peculiar gap, but didn't immediately recognize its cause. Some wondered if there might be something special about the galactic plane that prevented galaxy formation nearby, or if perhaps galaxies were somehow repelled by the gravitational influence of the Milky Way. It took careful study of interstellar extinction and the realization that dust was ubiquitous in the galactic plane before the true explanation became clear. The gap wasn't real. It was an observational artifact, a shadow cast by our own galaxy's dust. The consequences of this obscuration have been profound throughout the history of astronomy. One of the most dramatic examples involves our view of the galactic center itself. The heart of the Milky Way, located about 26,000 light-years away in the direction of the constellation. Sagittarius is home to hundreds of millions of stars, dense star clusters, massive molecular clouds, and at the very center, a supermassive black hole called Sagittarius A star, with a mass of about 4 million times that of the Sun. But in visible light, we can't see any of it. The dust along the line of sight is so thick that it dims visible light by about 30 magnitudes. A magnitude is a logarithmic measure of brightness. Each magnitude represents a factor of about 2.5 in brightness. 30 magnitudes means the light is dimmed by a factor of 10 to the 12th power, 1 trillion. A star that would appear bright enough to see with your naked eye if the dust weren't there becomes utterly invisible, fainter than anything even the most powerful optical telescopes can detect. For centuries, this meant the galactic center was a complete mystery. Early astronomers looking at the Milky Way stretching across the night sky could map the distribution of stars they could see, but they had no idea where the galaxy's true center lay. They couldn't penetrate the veil of dust to see what was hidden behind it. The actual structure and dynamics of the galaxy remained unknown, subject to speculation and educated guesses based on indirect evidence. The breakthrough came with the development of infrared astronomy. Infrared light with wavelengths longer than visible light can penetrate dust much more effectively. The amount of extinction drops dramatically at infrared wavelengths instead of 30 magnitudes of dimming. In the visible, you might have only 2 or 3 magnitudes in the near infrared, and even less at longer wavelengths. Suddenly, the galactic center became accessible. In the 1960s and 70s, infrared surveys began revealing the hidden structure of the galactic center. Astronomers could see dense concentrations of stars trace the spiral arms and map the distribution of dust and gas. And at the very center, they found something extraordinary: a bright, compact radio source, Sagittarius A star, that would eventually be identified as a supermassive black hole, the gravitational anchor around which the entire galaxy rotates. Radio astronomy provided another window through the dust. Radio waves have even longer wavelengths than infrared light, and they pass through dust almost unimpeded. Radio telescopes could map the distribution of hydrogen gas, trace the motions of molecular clouds, and study the magnetic fields threading through the galactic disk. Combined with infrared observations, radio astronomy revolutionized our understanding of the Milky Way's structure, revealing a complex, dynamic environment that had been completely hidden in visible light. The lesson here is humbling. For most of human history, we've been observing the universe with visible light, the only part of the electromagnetic spectrum our eyes can detect. And what we've seen has been systematically biased by dust. The brightest, hottest stars are dimmed and reddened. Entire regions of active star formation are hidden. The galactic center is invisible. Distant galaxies behind dusty lanes disappear from view. We were looking at the universe through a filter, seeing only what dust allowed us to see, and mistaking that filtered view for reality. Think about the implications of this. How many discoveries were delayed by decades or centuries because dust hid the evidence? How many astronomical phenomena went unnoticed because they occurred in dusty regions? How many galaxies, clusters, and cosmic structures remain undiscovered even now, lurking in the zone of avoidance, waiting for sufficiently sensitive infrared or radio observations to reveal them? The most dramatic dusty obscuration in the night sky is visible to anyone with dark skies and clear weather. The Great Rift, that dark lane we mentioned earlier, splitting the Milky Way from Cygnus down through Sagittarius. Stand outside on a summer night away from city lights and look up. The Milky Way stretches overhead, a luminous river of stars. But running through it like a shadowy canyon is a dark band where stars seem to disappear. Early astronomers lacking telescopes and spectroscopy didn't understand what they were seeing. William Herschel, the 18th century astronomer who discovered Uranus and conducted extensive surveys of nebulae and star clusters, observed these dark regions and called them holes in the sky. He thought they might be actual voids, tunnels through the distribution of stars, where for some unknown reason stars simply didn't exist. He could even see through these holes. He thought to the empty space beyond, to the edge of the stellar universe. Herschel was seeing accurately, but interpreting incorrectly. Those dark regions aren't holes, they're the opposite. They're some of the densest accumulations of matter in the galaxy molecular clouds, so rich with dust that they block the light from millions of stars behind them. Far from being empty, they're full of potential sites of active star formation nurseries where new stars are being born even as we look at them, hidden from our eyes, but glowing brightly in infrared and radio wavelengths. The misunderstanding persisted well into the 20th century. Even as late as the 1920s, some astronomers still referred to these features as dark nebulae, without fully understanding that they were caused by absorption rather than absence. It was the work of astronomers like Robert Trumpler, studying open star clusters in the 1930s, that definitively established the presence of widespread interstellar extinction and proved that dust was responsible for these dark features. Trumpler's method was elegant. He studied the apparent sizes and brightnesses of open star clusters at various distances. If space were truly transparent, clusters of similar physical size should appear smaller and fainter at greater distances in a predictable way. But Trumpler found that distant clusters appeared fainter than they should based on their angular sizes. Something was dimming the light from distant clusters more than geometry alone could account for. That something was dust. His work provided quantitative evidence for interstellar extinction and allowed astronomers to begin correcting their observations for dust absorption. But correcting for dust isn't straightforward. The amount of extinction varies enormously from place to place in the galaxy. Some lines of sight pass through relatively clear regions with little dust. Others pass through dense molecular clouds with extreme extinction. The distribution of dust is patchy, clumpy, concentrated in the spiral arms, and in specific cloud complexes. There's no simple formula that tells you how much dust lies between you and any given star or galaxy. Astronomers have developed sophisticated techniques to estimate extinction. One method uses the colors of stars. If you know what color a star should be based on its spectral type, essentially its surface temperature, and you measure what color it appears to be, the difference tells you how much the light has been reddened by dust. This technique works well for individual stars, but requires accurate spectroscopic information. For large-scale surveys, astronomers often use statistical methods analyzing the colors and brightnesses of many stars in a region to build up a map of dust distribution. Missions like the European Space Agency's Gaia satellite, which is measuring the positions, distances, and motions of over 1 billion stars in the Milky Way, are also providing unprecedented dust maps. By comparing the intrinsic brightnesses of stars estimated from their spectra and distances with their observed brightnesses, Gaia is creating detailed three-dimensional maps of dust throughout the galaxy. These dust maps are invaluable. They allow astronomers to correct observations for extinction, to identify particularly dusty regions where observations might be unreliable, and to study the distribution of dust itself as a tracer of the interstellar medium structure. They reveal that dust is not uniformly distributed, but follows the galaxy's spiral structure concentrated in the arms, where gas is compressed and star formation is active. Yet, even with the best dust maps, some regions remain stubbornly opaque. The very densest molecular cloud cores, where the next generation of stars is forming, can have optical depths exceeding 10 or even 100 magnitudes. At those levels, even infrared light struggles to penetrate. Only the longest infrared wavelengths and radio waves can see all the way through. This is why modern observatories observe across the entire electromagnetic spectrum. Visible light telescopes show us hot stars and the optical glow of nebulae. Infrared telescopes peer through dust to reveal star-forming regions in the galactic center. Radio telescopes map cold molecular gas and see through the thickest clouds. X-ray telescopes detect high-energy phenomena like supernova remnants and accretion onto black holes. Ultraviolet telescopes study the hottest stars and trace the ionization of gas. Each wavelength regime reveals something that others miss, and together they build a complete picture of a universe that dust both hides and reveals. There's a certain poetry to this. Dust created by stars scattered through space, participating in the formation of new stars and planets, also acts as a filter, a selective veil that determines what we can and cannot see. It's as if the universe is playing a cosmic game with us, hiding some of its secrets behind curtains of dust, while offering others freely to our view. And our ingenuity as a species is measured in part by how effectively we can peer behind those curtains using new technologies and new wavelengths of light to reveal what was hidden. Have you ever wondered what the night sky would look like if dust didn't exist? If the interstellar medium were perfectly transparent, the Milky Way would be unimaginably brighter, a blazing band of hundreds of billions of stars, visible all the way to the galactic center. We'd see distant galaxies more clearly, their structures unobscured by foreground dust. The zone of avoidance would disappear, revealing the full distribution of galaxies around us. But we'd also lose something: the beauty of dark nebulae, the mysterious shadows of molecular clouds, the way dust scatters light to create reflection nebulae. The universe would be different, perhaps less textured, less layered with mystery. But dust does exist, and it shapes not just what we see, but how we understand the cosmos. It forced us to develop new observational techniques to build telescopes sensitive to infrared and radio wavelengths, to create sophisticated models of extinction and scattering. It taught us that the universe is richer and more complex than what meets the eye. That reality extends beyond the narrow band of wavelengths we evolved to see. And in learning to see through dust, we've discovered something profound: that obstacles can be opportunities, that limitations can drive innovation, and that the act of uncovering what's hidden is one of the most human and most scientific endeavors we can undertake. Dust may obscure the universe, but in doing so, it also invites us to look deeper, to question what we see, and to never accept that what's visible is all that exists. Which brings us to the final, most personal part of this story: the realization that dust isn't just out there in the space between stars or orbiting the sun. It's here in you, in every atom of your being, connecting you physically and materially to the cosmos in ways both ancient and ongoing. Take a deep breath. Hold it for a moment. Now, exhale slowly. In that single breath, you just exchanged atoms with the universe. Oxygen molecules that were once part of ancient seas, carbon atoms, forged in the cores of dying stars, nitrogen created in supernova explosions. Every inhalation connects you to cosmic processes that span billions of years and trillions of miles. You are not separate from the universe observing it from a distance. You are the universe experiencing itself through human consciousness. And the bridge that connects you to the stars, the physical link between your body and the cosmos, is cosmic dust. Those same microscopic grains we've been following through their extraordinary journey from stellar deaths to planetary births to ultimately life itself. The story of cosmic dust is, in the most literal sense, your story. Let's trace it one final time from beginning to present and understand just how intimately you are woven into the fabric of the cosmos. 4.5 billion years ago, in a relatively unremarkable region of the Milky Way, a molecular cloud began to collapse under its own gravity. This cloud was already enriched with heavy elements: carbon, nitrogen, oxygen, iron, magnesium, silicon, created by previous generations of stars and scattered into space as cosmic dust. Some of these dust grains were freshly formed, condensed in the winds of red giants or in the debris of recent supernovae. Others were ancient presolar grains that had journeyed through space for billions of years, survivors from stars that died long before our solar system existed. As the cloud collapsed, that dust played the essential roles we've discussed, cooling the gas through infrared radiation, providing surfaces where molecular hydrogen could form, serving as the condensation nuclei around which larger structures would grow. The cloud fragmented, and at the center of one fragment, our sun began to form, surrounded by a swirling disk of gas and dust, the solar nebula. In that disk, dust grains collided, stuck together, grew. Micron-sized particles became millimeter-sized aggregates. Millimeter pebbles became centimeter rocks. Through countless collisions over millions of years, these growing bodies swept up more and more material, their gravity strengthening as their mass increased. In the inner solar nebula, where temperatures were high, the dust was primarily silicates and metals, materials that could remain solid even close to the sun. Further out beyond the snowline, water ice condensed onto grains, making them stickier and more massive. Eventually, these growing planetesimals, kilometer-sized bodies, began to dominate their orbital zones. The largest among them attracted more material through gravity, growing faster and faster in a runaway process. In the inner system, rocky protoplanets formed: Mercury, Venus, Earth, Mars. In the outer system, massive cores of rock and ice grew large enough to gravitationally capture hydrogen and helium gas, becoming the gas giants Jupiter and Saturn, and the ice giants Uranus and Neptune. Earth 4.5 billion years ago was a molten ball of rock heated by countless impacts, and by the decay of radioactive elements in its interior. Over millions of years it cooled. A solid crust formed. Water vapor in the atmosphere condensed and fell as rain, creating the first oceans. The heaviest elements, primarily iron and nickel, sank to the center, forming Earth's metallic core. Lighter silicate minerals floated to the surface, creating the mantle and crust. And every element in that process, the iron in the core, The silicon and oxygen in the rocks, the carbon dissolved in the early oceans, came from cosmic dust. Not metaphorically, literally. The atoms in Earth were once grains of dust orbiting the young sun. And before that, they were ejected from dying stars. And before that, they were synthesized in stellar cores through nuclear fusion. Life emerged on Earth remarkably quickly, geologically speaking, within the first billion years of the planet's existence, possibly even earlier. The exact mechanism remains one of science's great unsolved mysteries, but we know that life is built from the same elements that dominate cosmic dust: carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. These are sometimes called the CHNOPS elements, and they're the foundation of all biological molecules, proteins, nucleic acids, lipids, carbohydrates. Where did Earth's organic molecules come from? Some were certainly synthesized on Earth itself, in the early oceans, or in hydrothermal vents through chemical reactions driven by lightning ultraviolet radiation or geothermal energy. But a significant fraction may have been delivered from space carried to Earth by comets and asteroids rich in organic compounds that formed on the surfaces of dust grains and cold molecular clouds and were preserved in comets for billions of years. We know this is plausible because we've detected complex organic molecules in comets, in meteorites, and in interstellar dust. The Murchison meteorite, which fell in Australia in 1969, contains more than 70 different amino acids, including many not found in terrestrial biology. These amino acids formed in space probably through reactions on dust grain surfaces and survived the formation of the meteorite's parent asteroid, the asteroid's journey through space, and the meteorite's fiery entry into Earth's atmosphere. So, when the first self-replicating molecules appeared on Earth, the ancestors of DNA and RNA, they were built from atoms that had once been cosmic dust. And as life evolved, diversified, and spread across the planet, every living thing from bacteria to redwood trees to blue whales to you inherited that cosmic legacy. Let's make this concrete and personal. Your body contains roughly 7 octillion atoms. That's 7 followed by 27 zeros. A number so large it's almost meaningless to contemplate. But we can break it down by element. About 65% of your body mass is oxygen, mostly in the form of water. 18% is carbon, the backbone of organic molecules. 10% is hydrogen. 3% is nitrogen. 1.5% is calcium, mostly in your bones. 1% is phosphorus, crucial for D, Na, and ATP. And there are traces of sulfur, potassium, sodium, chlorine, magnesium, iron, and dozens of other elements. Every single one of those atoms, except for most of the hydrogen, was created inside a star. Hydrogen is primordial, formed in the Big Bang, about 13.8 billion years ago. But everything else, the carbon in your DNA, the nitrogen in your proteins, the calcium in your bones, the iron in your blood, was forged through stellar nucleosynthesis. The nuclear fusion reactions that power stars and in their deaths create heavy elements. The oxygen you breathe right now, it was created inside massive stars, more than 8 times the mass of the sun, through the fusion of helium and carbon in their cores. When those stars exploded as supernovae, they scattered that oxygen into space as cosmic dust, silicate grains, and water ice, which eventually found their way into the molecular cloud that formed our solar system. The carbon in your body, the element that makes organic chemistry and life possible, was created primarily in red giant stars through the triple alpha process where 3 helium nuclei fuse to form a carbon nucleus. These stars shed their outer layers as stellar winds rich with carbon dust, enriching the interstellar medium with the raw material for future life. The iron in your hemoglobin, the protein that carries oxygen in your blood, giving it its red color, that iron was created in the cores of massive stars during the final stages of nuclear burning, and it was scattered into space when those stars exploded as Type II supernovae. The iron atoms in your blood are literally pieces of exploded stars, incorporated into dust grains, swept up into the solar nebula, accreted into Earth, weathered and cycled through geological processes, taken up by plants, consumed by animals, and eventually becoming part of you. Carl Sagan famously said, "We are made of star stuff." He was right, but let's be even more specific. We are made of stardust. The atoms in your body didn't travel directly from stars to you. They traveled as dust-solid grains of silicates, organics, and ices drifting through space for millions or billions of years, participating in the cosmic recycling program that creates new stars and planets from the ashes of the old. And this isn't ancient history. It's ongoing. Right now, as you listen to these words, cosmic dust is falling to Earth about 40,000 tons per year, remember? And some of that dust over time will be weathered and dissolved, its atoms entering the biosphere, taken up by plants, consumed by animals, and eventually incorporated into living organisms. The boundary between space and Earth, between the cosmos and life, is porous and active. There's something profoundly moving about this realization. It dissolves the false separation we often feel between ourselves and the universe. We think of space as out there distant and cold, while we are here warm and alive. But that distinction is an illusion. The atoms in your body have been out there. They have orbited other stars, drifted through interstellar space, condensed into dust grains, been irradiated by cosmic rays, coated with ice in molecular clouds, heated in the solar nebula, incorporated into Earth, weathered by rain and rivers, and finally assembled into the temporary pattern that is you. You are a collection of recycled stardust, a transient arrangement of atoms that were old when Earth was young, that will persist long after you're gone, moving on to become part of new structures, new planets, perhaps eventually new living beings. There is no you separate from the universe. There is only the universe endlessly rearranging itself, and sometimes in rare and precious moments, becoming conscious enough to contemplate its own existence. This perspective, what Carl Sagan called the cosmic perspective, has practical implications too. It reminds us of our unity as a species. The atoms in your body and the atoms in every other human being on Earth came from the same cosmic sources, forged in the same stellar furnaces, scattered by the same supernovae. We are quite literally made of the same stuff, siblings in the deepest possible sense, children of the stars. It also reminds us of our responsibility. Earth is not just our home, it's a rare and precious oasis where stardust has become complex enough to ponder its own origins. The conditions that allow life to exist are fragile, dependent on a delicate balance of temperature, atmosphere, water, and chemistry. We have a duty to preserve this world, not just for ourselves, but for all the living things that share our cosmic heritage. And it reminds us of our smallness in time and space, but also our significance. Yes, we are tiny specks of dust on a pale blue dot orbiting an average star in an ordinary galaxy among hundreds of billions of galaxies. But we are also extraordinary conscious matter, stardust that has evolved the ability to understand where it came from, to study the universe, to create art and music and science, to love and dream and wonder. That is not diminished by our cosmic origins. It is elevated by them. The journey of cosmic dust from stellar deaths to planetary births to conscious life is one of the most beautiful stories science has ever uncovered. It's a story of cycles and connections of matter, endlessly transforming, while information and complexity gradually increase. It's a story that connects the largest structures in the universe to the smallest particles that links the distant past to the living present. And it's a story that's still being written. Astronomers continue to study cosmic dust with ever more sophisticated instruments. The James Webb Space Telescope revealing dust in the earliest galaxies. ALMA mapping dust in protoplanetary disks with unprecedented resolution. Sample return missions bringing extraterrestrial dust back to Earth for analysis. Each discovery adds a new chapter, deepens our understanding, reveals new mysteries to explore. But perhaps the most profound part of this story is that you are part of it. Not just as an observer, learning about dust from a distance, but as a participant, a living embodiment of the cosmic dust cycle. The atoms in your body have journeyed across space and time to be here now, arranged in this particular pattern that allows you to think and feel and experience the universe. When you look up at the night sky, you're not looking at something separate from yourself. You're looking at your origins, your family, your home. The stars that shine overhead are your ancestors, the furnaces where your atoms were forged. The dust that drifts between them is your siblings, future building blocks of planets and life. And Earth, this beautiful blue world, is where your particular arrangement of stardust happens to reside for this brief moment in cosmic time. So, rest now knowing that you are connected to everything that you are part of, an ancient and ongoing process that stretches from the Big Bang to the present and will continue long into the future. Close your eyes and feel the atoms in your body humming with quantum uncertainty held together by electromagnetic forces, each one a tiny fragment of stellar history. You are stardust conscious and aware a way for the cosmos to know itself. And perhaps, as you drift towards sleep, you can take comfort in the fact that you are never alone, never separate, never disconnected from the universe. You are the universe experiencing a human life. And when this life ends, your atoms will continue their journey, returning to Earth eventually, to the cosmos, ready to become part of new stars, new planets, perhaps new life. The cycle never ends. Creation, destruction, transformation, written in particles so small we can barely see them, yet so essential that without them, nothing else would exist. The smallest things indeed build the universe, and they built you. Thank you for joining us on this journey through the cosmos, exploring the smallest particles that create the largest wonders. If you've enjoyed this exploration of cosmic dust and the profound connections between stars and life, we'd love to have you back for our next story, where we'll continue uncovering the gentle mysteries of the universe, one wonder at a time. Until then, sleep well, Stardust. The universe dreams through you.